All right, so this video is going to cover heat transfer. It'll cover kind of an overview and the three main types, and then it'll also kind of go a bit more into a deep dive on conduction. And that's because conduction, if you're doing heat transfer in your job, most likely it's conduction. Okay. To do that, I've got kind of a big problem that involves all three types of heat transfer. So what are the three types? So there's conduction. So that's heat moving through something. So in this case, in this problem, I have a window. So we've got the window here. So heat moving through something. Next type is convection. And that is a fluid flowing over a surface and heating it up because one is at one temperature and one's at a different temperature. So in this case, we have wind. So wind is flowing over the window on the outside, and it is going to heat it up. And the third type is radiation. So for example, that's the heat that we feel from the sun. So the sun emits radiation heat, and in this case, it would heat up the outside surface of the window. So what is this problem? So we can measure the inside temperature of the window because we could just stick a temperature probe on it. We want to calculate the outside temperature of the window, so this temperature. So step one is the same step one that you use in like any class, and it is to write out an energy balance. So I'm gonna zoom in right here. So what do we have entering and leaving? Right there. So we talked about conduction. So that's heat going from the outside surface to the inside surface, assuming the outside surface is hotter, which I'm going to assume. Even if it's not, as long as you keep your sign convention consistent, it will return a negative number, and then you'll know what that means. But anyways, okay. So we've got a couple things entering and leaving. We start with conduction. So it's going from this point that way. Could be going the other way, but like I mentioned, it'll just turn out negative. So what is the equation for this? So the equation for heat, Q, or energy, is delta T over R total. This R is the thermal resistance. And this is kind of what I'll deep dive into after we kind of go through this example problem. But for now, it's pretty straightforward. So delta T, I'm going to say it's T minus T inner over R total. For conduction through a surface, R total is just R conduction. And the equation is L over KA. So what is L? L is this distance between like the thickness of the window. K is the thermal conductivity of the window. It is basically how much heat can the window absorb before it heats up by 1 degree. And you could literally Google it. It's like a constant that you can find online. And A is the area. And like, for example, we'll draw the window into the page, and that would be the area. We'll see later on, though, that it cancels out, and we solve for heat per unit area. But anyways, cool. What is the next piece of energy? So next we have, let's do the convection. So we have the T wind and T, okay. So I'm gonna assume, again, that T wind is greater than the outside temperature of the window. So heat always goes from hot to cold. So I'm gonna assume that it'll go from the wind to the window. So I'll write it so that that number is positive. So we've got something over here. Q equals delta T over R total, which equals T wind minus T over R total for convection is just R convection, which is 1 over HA. Cool. And H is, so K was the thermal conductivity of the window. H is kind of how well heat can be transferred from the fluid to the window. And there are approximation ways to calculate it. But if you really want to get a good number for H, you've got to do experiments. But you can kind of approximate it. But usually, like on an exam or something, it'll be given to you. And A, it's the same area as over here. All right, now we've got radiation. So we've got radiation from the sun to the window. And the sun, I think if you do the math, you get the sun's temperature is like 5,000 Kelvin. So definitely heat is going from the sun to the window. Okay, radiation, you can write it in a delta T over R total way, but I'm not going to because it's more complicated. The better way to write it is this is the better way to write it. Okay, so for convection and conduction, we just had like temperature to the first power. For radiation, it's temperature to the fourth power. So a sun that's at 5,000 Kelvin to the fourth power, that's a huge number. And chances are this sun will this value will be so much greater than this value that it can cancel out. But I'm gonna just include it because it's proper to include it. Okay, what is this alpha and this sigma? All right, the sigma is a constant. I think it's Boltzmann constant or something. What is the number for it? You can literally Google it. 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the 4. But anyways, it's just a number. You can Google that Boltzmann constant online. This alpha is how well the window absorbs heat. And I wrote it up here because we'll assume that we know what that number is. You know how if you wear like a black shirt, you'll outside, you'll feel hotter than if you wear a white shirt. And that's because black shirts are better at absorbing heat than white shirts. White shirts reflect a lot of the heat. But anyways, so this alpha is how well the window surface absorbs heat. This is T sun and this is T window. Okay, and then the last thing is, I debated whether or not to include it, but I'll just include it because some places want you to include it, some places don't really care. This T sky. So what is this? So just like the sun is radiating heat to the window, the window also radiates heat back out to its surroundings. Maybe it's better if I say surroundings. So this could be radiating heat to a building across the street, could be radiating heat to the grass, to the tree, whatever. Yeah, so we're just going to assume that all of those things are at a constant temperature. So let's say, like, what's the weather today? I don't know what the weather today is, but let's say it's like 80 degrees Fahrenheit. You'd probably set T surrounding at 80 degrees. And I'm going to assume my sign convention is going from the window to the surroundings. And it is literally this exact same equation. Except we have emissivity instead of absorptivity, but I'll explain that in a second. All right, so absorptivity was how well something absorbs heat. Emissivity is how well something repels heat, I guess. And you can measure both of those like in a lab for a surface. Cool, so this is our energy balance. We have two things entering. We have two things leaving. So if we wrote it, ooh, I forgot one thing. So this is a unitless number. This is watts per meter squared Kelvin to the fourth. These are Kelvin to the fourth. So I'm missing a meter squared. That is because I forgot to multiply these by area. Okay. Cool. So our energy balance, I'm going to write it as stuff going in equals the stuff going out. So the stuff going in, we can move this up to the top. We'll have HA T wind minus T plus another thing going in, A alpha sigma T sun to the fourth minus T to the fourth equals the stuff going out, which is this and this. All right, so everything in this equation is known except for T. And we could just solve for T. But before that, like I mentioned before, the areas can cancel out. So we just solve for, instead of solving for total heat, we solve for heat flux, which is heat per unit area. And you'll hear heat flux a lot in heat transfer. But yeah, so those are literally the main equations for heat transfer, all in one problem. Now, let's do a bit of a deeper dive into conduction. Okay, so a lot of buildings, including my work building and my apartment building, they use two windows. So like this is the outer window, and this is the inner window. And there's literally an air gap in between them. And why do they do that? So back here, we had the total heat entering was delta T over R total. And R total was just one window. It was LKA. But now, R total would change if we have multiple windows with an air gap. So what would that be? What's a good way to write this? Yeah, let's go with that. So our total would be the two windows, so it'll be 2 times L over KA plus the convection in between, 1 over HA. So right away, this will be a bigger number than this, even without plugging in numbers. And if you increase the R total, you decrease the amount of heat that can go through that. So by adding more windows, or by adding thicker windows, or by increasing the thickness, or adding more windows, you can decrease the amount of heat that goes through. So right away you can keep yourself cooler by installing thicker windows, or by installing an air gap in between 2 sets of thinner windows. Okay. There's some pretty neat things that you can do with with thermal resistance. So you're going to hear this pretty early on in your class. You can write this out as a thermal resistance network. And just like in circuits, or what's the other class? Like physics 2, where they go into electricity and resistance and voltage and current and all that stuff, you can literally use those exact same principles here. So we've got a couple different thermal resistance things. So we've got a thermal resistance of convection between the air, T, is that what I called it over here? T wind. You've also got the conduction resistance. You've also got another convective resistance. You've got another conduction resistance and another convective resistance. In this case, we measured this temperature, so we ignored this, but you can include it if you want. If you're measuring the inside of the room temperature, you can do that. And the math will still work out. Okay. I guess the last thing would be, well, okay, to finish this off, the difference between what I drew up there and this equation. So you have these 3, which is from here down to here. You would add 2 more convective. So 1 over HA plus 1 over HA. These 3 H's would be different. One of them would be from the wind to the window. One of them would be between the windows. One of them would be the window to the inside of the room. Probably these 2 would be similar, but this one will for sure be different because the wind is moving. Okay. And then what you could do is, if you know T wind, and you know, for example, the outer temperature of the window, you could do Q, so the heat going from the wind to the outer surface of the window equals delta T over just this resistance, which will be 1 over HA. And you can solve for that, because let's assume you know both temperatures and you know all this stuff. So this will get you a number. And then, since the amount of heat entering the outer surface of the window, it has to go through the window all the way to the other side. So it has to go all the way through. You can say this same Q also equals T wind, T room, minus T room over R total, where R total is this. I don't think I explained that super great, but I think I explained that well enough to where I can remember in the future. Anyways, the last thing is, so all this math works out great if you have like square windows or rectangular windows, but what if you have you wouldn't have round windows, but let's say you had a pipe and there's air transferring heat to the pipe on the outside. The heat goes through the pipe and then it goes to heat up water on the inside of the pipe, or some fluid on the inside of the pipe. So how would you do, what's the right word for it? I'm gonna just say round. How would you do round heat transfer? The convection equation is the same, so 1 over HA, but for A, you would have to do, well, okay, what would be going on here? R total would equal that plus conduction plus another convection. So what would this A be? This A would be 2 pi R, let's say it is the pipe has a depth of L. So 2 pi RL, and this is R outer. And this would be your area. So it's the same exact equation as over here, but your area would change because now you're dealing with circles. Plus this conduction. What's the equation for that? It is natural log R outer over R inner over 2 pi KL. We know what this K and the L are. K is thermal conductivity and L is the thickness. No, L is not the thickness. L is the same L as over here, which is the depth. Plus the last convection, which would be 1 over H. And for area, it would look like this, except we would use R inner. Cool. Cool. That is literally it. That is kind of all the main parts of heat transfer. You can dive more deep into, so this is a tube problem. What if you have finned tubes? You could dive more deep into that, and fin tubes are used in industry. I use them at my job all the time. And there are equations for that. There's more equations for radiation, but they're kind of boring. And then there's different approximation equations to calculate convection coefficients based on like the velocity of the fluid, the Reynolds number, geometry of what the fluid's going over, whether it's a flat plate, pipe, sphere, or internal flow. That's fine. That stuff is kind of boring. This is the main part of heat transfer. But yeah, so we covered different types. So convection, like the wind, conduction, like through the window, radiation, like from the sun into the surroundings. We went through how to make an energy balance. Went through thermal resistances and resistor networks. And we also went over circular conduction. I think that's about it for this video. Cool beans.